Hi guys, welcome to Calculus Crush. Today we're going to be doing an optimization problem. What we're going to do is find the area of the largest rectangle that you can draw inside of an ellipse. This is just your standard equation for an ellipse. It's not the most general equation, but it's pretty close. We know it's an optimization problem because they're asking for some kind of superlative. For example, largest, smallest, fastest, shortest, highest. We're trying to maximize or minimize something. In this case, it's the area of a rectangle. So let's start by drawing an ellipse. I've got some stuff prepared already because it's a little bit hard to draw straight lines. So here's our XY axis. Now let's draw the ellipse. And now let's inscribe a rectangle in that ellipse. So we need to write down the formula for the area of this rectangle, take the derivative of it, set it equal to 0, and then determine the dimensions, which will make the biggest area. So we can see another example of a rectangle that we can draw in here. It would be something like this. Very, very thin little one up here. Now, obviously, this probably wouldn't give us our maximum area. Neither would a rectangle like this. So it's probably going to be some, it's obvious that there is some optimum dimensions to get the biggest rectangle possible. And we're going to figure that out. So let's write down the area of this blue rectangle. So the area of a rectangle is just base times height. So the base would be this length here. Now what would that be? Well, this point here is a point on the ellipse, which will have the values x and y. So the base, half of the base is just x. So if we go 2 times x, we get the base. And the height, well, the height is just this bit here. Now we know that this point is xy. And so this distance here is y. This is also y, so it's times 2y. So altogether, it's 4xy. Now this equation is written in terms of 2 variables, x and y. We need to write it in terms of 1. So why don't we solve y for x using this equation that was provided, the equation of the ellipse? So the area is equal to 4x times y. Now let's solve for y up here. Y is equal to 1 minus x squared over a squared times b squared. And we have to take the square root of that. So that's just equal to b times 1 minus x squared over a squared square root. So we substitute in that value for y, and what we get is b times 1 minus x squared over a squared square root. So this is the formula for the area. I'm just going to put a little box around it because it's an important formula. Now what we need to do is calculate a prime. But before we do that, I'm going to rewrite this getting rid of the root sign. And I'm going to put the b right at the front. So x times 1 minus x squared over a squared. And this is to the power of a half. The square root is the same thing as the power of a half. Now this is an easier way to write it if you're going to take the derivative. This is always a nicer way. It's nicer to write it with square root signs, but when you take a derivative, you need to use a power rule. You need to have those powers in terms of fractions. So let's take the derivative. A prime is equal to 4b. Now what we have here is the product rule, which is the derivative of the first times the second. So I'll use big brackets. The derivative of the first, derivative of x, is just 1 times the second, 1 minus x squared over a squared to the power of a half, plus the first, which is x, times the derivative of the second. The derivative of this function here, we have to use the chain rule. So the 1/2 comes down in front, times the inside to the power of minus 1/2 times the derivative of the inside, which is minus 2x over a squared. So this is our derivative. Let's do some work in simplifying it now. So what's common between these two? Well, actually, let's take one more step just to write it out and get rid of some terms. We don't need the 1 here anymore. Now we've got a minus 2x, we've got a 1/2, and we've got an x. So that'll give us a minus x squared over a squared. 1 minus x squared over a squared to the power of minus 1/2. Now we can factor out what's common between these two, and we can pull out a 1 minus x squared over a squared to the power of a minus 1/2. We have to take out the smallest one. We've got a 1/2 here, and we've got a minus 1/2. Minus 1/2 is smaller than a 1/2. So what we're left over with is 1 minus x squared over a squared to the power of 1, because you pulled out a minus 1/2. So minus a minus 1/2 is plus a 1/2, minus x squared over a squared. So let's write the final expression for this derivative. So I'm going to put this on the bottom, and I'm going to write it later. We've got 1 minus 2x squared over a squared divided by, since this is to the power of minus 1/2, it'll go down to the bottom, x squared over a squared, and I'm going to restore the root sign. So this is a nice tidy expression for the derivative of the area. Now that we have the derivative of the area, this is where the optimization comes into play. We want to set this equal to 0 and solve for x, and that will tell us at what x value we have a minimum or maximum area. We'll need to figure out if it's a minimum or maximum. Now what can make this derivative equal to 0? Can we ever make something equal to 0 using the bottom? No, we can't. So we don't even need to worry about this part. The 4b will also never be 0. So the only thing we need to set to 0 is this term right here. 1 minus 2x squared over a squared equals 0. We just need to solve this. So if we solve for x, we get a squared over 2, and that whole thing is square root, which is equal to a over square root of 2. So when x is equal to a over the square root of 2, we have a minimum or maximum area. Now let's first of all figure out if this is a minimum or a maximum. So we've got a number line. Let's draw the roots of our equation on this number line. A over the square root of 2. And what we need to do is check the sign of the derivative before and after. So if we look at a number less than a over 2, for example 0, and we plug 0 in for x in our derivative, so this whole term becomes 0, and we just have 4b on the top. And then this whole term becomes 0, and we've got 1 on the bottom. So it's just 4b. That's positive. Now over here, if we use a number bigger than a over 2, so let's use a, for example. A is larger than a over the square root of 2. So if we use a, we get 2a squared. If we divide by a squared, then it's just 1 minus 2 in here, which is a negative number. And down here we have 0. Well, a doesn't work very well either. Well, you can convince yourself that it's going to be negative here. We sort of showed it. I mean, if you think about it, down here is always positive. Up here, we found a was making it negative. So if we use a number just slightly less than a, it'll still be negative. So that means our function is increasing. And then we get to 0. And then it starts decreasing. So we know we have a maximum. So when x is equal to a divided by the square root of 2, we have maximized the area. Now let's figure out what is the maximum area. So we have the dimensions. X. Okay, we have one of the dimensions. X equals a over root 2. Let's figure out the other dimension. We have a formula for y up here that we derived. So y is equal to b 1 minus, now when x is a over the square root of 2, we have a squared over 2a squared, which is equal to b times 1 minus 1/2 square root, which is equal to b over root 2. Let's write that down for the dimensions. So the dimensions of the square, the dimensions of the rectangle, the base is going to be this distance, which is 2 times x, 2a over root 2, which is equal to root 2a. And then the height will equal 2 times y, which is 2b over root 2, which is root 2b. That a and b are not under the root sign. So those are the dimensions. That's the first part of the problem done. Now that we know the dimensions, what is the area? Well, the area is just the base times the height. So we can use root 2 times a times root 2 times b, and what we're left over with is 2ab. So maybe I'll call that a max. There you have it. We've determined the maximum area of a rectangle drawn within an ellipse, and it's equal to 2 times AB. We've also figured out the dimensions of that rectangle. So the base would be root 2 times A, and the height would be root 2 times B. Okay guys, thanks for watching. Until next time.